Good morning, everyone. My name is Mohammad Tala, student of M.Sc. Applied Geology, final year, Department of Earth Sciences, Indian Institute of Technology, Roorkee. Today, we'll be exploring the fascinating world of linear structures in geology, their type, formation processes, and their importance in interpreting deformation history. So let's start. Talking about the lineations. Lineations are linear features in rock where one dimension dominates. They are key to understanding deformation, appearing in both metamorphic and igneous rock. For example, linear structures in gneiss show mineral alignment due to strain. As you can see in the first diagram, there is a development of lineations in gneissic body where they show mineral alignment due to strain development. Talking about the type of lineations, there are two type of lineations which are primary lineations, which also non-tectonic in nature, and the second one is tectonic, which is deformation related, or they develop due to the tectonic activity. Lineations can be primary, like lava flows, patterns, or tectonic formed during deformation. Penetrative lineations such as stretched minerals are pervasive, while slickened lines are restricted to fault surfaces. Talking about the significance, they helps in distinguish between primary and deformed induced structures. For example, intersection lineations, intersections between the bedding and the S1 foliation, so interaction of bedding and cleavage. Fabric elements in tectonic lineations. Tectonic lineations include physically elongated objects, intersections of planar objects, and geometric features like fold hinges. Talking about their significance, they help us map deformation phases. Intersections line, they are formed by two planar structures, cleavage bedding intersection as we have already seen in the first slide. The second one is geometric line linear features, which are fold hinges line and granulation axis. The main difference between lineations and lineaments are lineations are the small scale structures within rock, and on the other hand, lineaments are large scale linear features which can be seen on maps, satellite, etc. They often represent fractures, fault, or foliations intersecting surface. Examples and significance. Fold hinges and granulation axis, they indicate deformation history. Slicken lines, they reveal fault movement direction. And intersection lineations, they help interpret structural relationship. The nature of penetrative lineations, they formed exclusively during plastic and ductile deformation. They represent the dominant fabric element in the affected rock. They occurs where S fabric is weak and absent. Classifications of tectonites by fabric. There are three classifications. First one is L tectonite, the second one is LS tectonite, and the third one is S tectonite. L tectonites, they are strongly characterized by linear fabric, L fabric. They exhibit weak or absent planar fabric, S fabric. They correspond to constracial strength, which is x-axis is way longer than y, and y is equal to z in filling direction, as you can see in the uh, first diagram. In the first diagram, this is a cigar shape which is represented by the L tectonites, and the second one is LS tectonite. They display this balance between the both linear and planar features. They show intermediate strain. It is plotted near diagonal in Flynn diagram. They represent the most common fabric combination, and the last one is S tectonite, which is dominated by planar fabric, S fabric. They contain minimal or no linear fabric. They indicate flattening strain in Flynn diagram. Their interpretation, The fabric can tell us the deformation regime. L-tectonites, which represents the consortial strain elongation dominant. As you can see in the first diagram, elongation is dominant. LS tectonite is the plane strain, mineral lineations. Minerals and minerals aggregate can form a linear fabric by means of recrystallization, dissolution, precipitation, or rigid rotation. Mineral lineations form through processes like recrystallization, while ideal for strain analysis. Limitations like their initial shape. We don't know their initial shape, so it restricts us quantitative measurement. Formation processes of mineral lineations, physical rotations occurs when rigid prismatic minerals rotate in a soft matrix. For example, amphibole epidote crystals in mica schist. They are limited by the competence contrast between minerals and matrix. Synkinematic recrystallization, their primary formations mechanism is when rotation is insignificant. It involves the plastic deformation mechanism, dissolution precipitation process, precipitation pressure stain shadows, for example, quartz. And the second one is brittle deformation, which is crushing catalysis of brittle minerals in ductile matrix. It reshapes mineral aggregate into linear elements. The most important part is strain analysis using mineral aggregates. Spherical aggregate deform into strain ellipsoid shape due to deformation. They provide direct strain measurement when initial shape is known. If we know the initial shape, then we can directly measure the strain. It is the most reliable with minimal competence contrast. There are some challenges associated with us. If we don't know the original shape, we cannot quantitatively strain estimates. Fourth topic is stretching lineations. Stretching of minerals and mineral aggregate into a penetrative stretching. Lineations form the most common type of lineation in deformed metamorphic rock. Stretching lineations are linear structures defined by the shape of deformed object. For example, stretched pebbles and oolites. Stretching lineations like elongated pebbles provide strain data. However, competency contrast between minerals can complement analysis. For example, deformed conglomerate, flattened, stretched, and pebbles. Deformed oolite originally spherical, grains now elongated. Quantitative strain analysis. Stretching lineation provide quantitative strain data when original shapes we know, initially sphericals, oolites, and pebbles, which gets converted into the elliptical shape. Competency contrast should be minimal because if it is competency contrast is large, then it is uncertain. It used to calculate strain ellipsoid. Stretching lineations and shape fabrics are extremely common in plastically deformed rocks such as gneisses. As you can see in the diagram, stretching lineations in quartzite conglomerate. The long axis of the pebbles are plunging to the right. Talking about the rodding structures, elongated mineral aggregates like quartz rods in mica schist, gneisses. Their characteristics include distinct from host rock, cigar shape or rod-like. Cigar shape is elongated in one direction as we have already seen in the Flynn diagram. It is often interpreted as stretching lineations. The combination of bedding and cleavage S0 and S1 planar structures intersect, and the line of intersection is regarded as the intersection lineation. When the two planar structures like bedding and cleavage they intersect, and the intersecting line is called intersection lineation. They found on fractures where the main slip plane intersect secondary fractures. For example, Liddell fractures and tensile fractures. Common example include bedding S0 intersect tectonic cleavage S1, which create L1 lineation or the intersection lineation. The intersection of two tectonic foliations S1 and S2, it also creates intersection lineations. Their characteristic They are parallel to fold axial traces and hinge lines. Except, there is an exception. In transected fold, lineation may form an angle with the axial trace. As you can see in the figure, there is a hinge line. This is the axial surface, and they are the traces of cleavage. They may appear locally in some rocks as penetrative fabrics in most cases. As you can see in the second diagram, there is S0 or S1 intersection lineation, which is created by the or which is formed by the intersection of bedding and intersection S1 lineation, which create the L1. Their significance include they are important because they are the kinematic indicators in the deformed rock. They can be folded by later deformation event, providing evidence of polyphase deformation history. There are multiple deformation, so it can gives the deformation history of multiple deformation phases, and they also can provide the relative timing of structural events. Their field identifications involve visible on bedding planes where cleavage intersect them, as you can see in the 13.3 diagram. They used to determine fold orientation, reconstruct deformation sequence. They analyze the structural relationship between planar fabrics. They help track layer rotations. As talking about the transected fold, they hint at complex orientation. Fold axes are considered as linear structures, even though they are theoretically lines describe the geometry of folded surface. Their fabric formation, their high density of parallel fold axes can form a fabric. They are common in phyllosilicate rich rocks. They often occurs in metamorphic rock, uh, where small scale folds or granulation create a granulation lineation. And what is granulation lineation? Lineations. They are composed of numerous millimeter to centimeter fold hinges of low amplitude folds. They occurred in multiple deformed phyllites and schist, micaceous layer in quartz and schist, myelonites and gneisses. They are how they are distinct from the intersection lineations. Unlike intersection lineation, granulation lineations consist of visible fold hinges, which is recognizable to the naked eye. Their significance include they are comparing early granulation lineation with slightly younger fold axis and can reveal layer rotation during deformation. Relation to transected fold. A mismatch in the orientation between lineation and fold hinges suggests progressive deformation as you can see in the transected fold. Talking about the most important part is Bodinage and mullions. Bodins are competent rock layers that have been staged into segments. As you can see in the diagram also, this is the lineations. These are all the stress segment, cylindrical pinch and swell structures and Bodins. Bodins are stress segments of competent rock layer formed by extension, typically elongated in one direction, defining a lineation. Types and strain relation. Linear Bodins, they form when x-axis is longer than y-axis in a strain ellipsoid. Strong elongation in one direction. Tablet Bodins occurs when x-axis is equal to y-axis. Similar elongation in two directions. And their association with folding, they commonly found on fold limbs with long axis parallel to the fold axis, and their orientation, which can help the strain history during folding. Their recognition and limitation. They are best identified in cross section perpendicular to their long axis. Talking about the mullions and pencil structures, linear deformation structures restricted to interface between competent and incompetent rocks. Morphological characteristics, they exhibit cuspicate geometry with cusps constantly oriented toward the more competent rock, which means higher viscosity during deformation. Their wavelength is basically controlled by the viscosity contrast between layers. Talking about the mechanism, they develop through layer parallel shortening in response to viscosity contrast. They are similar to the buccal folds but differ in shorter wavelength. Their restrictions to single interface rather than affecting entire layers. As you can see in the diagram, this is the lineation part and incompetent and competent layer. Their geological occurrence includes commonly observed at quartzite phyllite or quartz mica schist boundary. They also found on surface of quartz pods within mica schist. Their interpretative significance, they serve as the indicator of rheological contrast during deformation. They provide constant on strain partitioning as lithological interface. Talking about the pencil structure, they formed from the interface between compaction cleavage and later tectonic cleavage. Two equally developed tectonic cleavages. Their characteristic, they exhibit preferent orientation defining a linear fabric. They are classified as a lineation in deformed rock. They typically developed in unmetamorphosed sedimentary rock, very low grade metamorphic rock. Their geological significance include they indicate overprinting, cleavage relationship, record progressive deformation in weakly metamorphosed setting. Striations or slicken lines. Slicken sides, the smooth striated slip surface often shiny and polished. They are they are generally 1 mm thick layer of crust, cohesive fault rocks. Their formation resembles glacially striated surface. Many slicken sites are later coated by mineral fill or actually consist of fiber lineations. In the first diagram, slicken sites with slicken lines formed by cataclastic shearings of epidote on a post-Calodian normal fault in the Precambrian. Geometric hysteria results from the regular corrugative slip surface morphology. Its preferred orientation aligned with slip direction. A special type, cigar-shaped lineation in deformed band cluster zones in the diagram. Coexistence of lineation type, geometric hysteria from surface shape often coexist with physical hysteria, slicken lines from abrasion. Talking about the lineations and kinematics, there is a relationship between the lineations and kinematic, and using the lineations, we can interpret the kinematics. Fault related kinematics, lineations as movement indicator. Lineations as movement indicator means lineations, by studying the lineation, we can interpret the movement of the fault. Lineations are important structures for understand the sense of movement of individual slip surface. The movement indicate fibers lineation, slicken lines. Slicken line, striae, and several other lineation associated with faults parallel the movement direction, but do not in themselves reveal the sense of shear. Geometric lineations, reliable sense of movement determine often requires additional information also. We cannot solely depends on the lineations for the movement direction. We required some other additional information for the uh, sense of movement. Their limitations, slicken lines, hysteria, other fault association lineation, they are the parallel movement direction. They do not reveal sense of shear. Determining of the sense of movement require additional information, which is fracture morphology relative to mineral growth, second order fracture geometry, correlation of marker across slip surface, observation of drag adjacent to fault. Lineation and kinematic in plastic regime. It occurs commonly structures in extensional shear zone, strike slip zones, and Sterane axis replace kinematic axis. Kinematic axis was abandoned in favor of a strain ellipsoid as XYZ. Simple shear stress lineation lies in XZ plane of strain ellipsoid. It rotates from 45-degree towards shear direction A axis with increasing strain. At high strain lineation A axis transport direction. Stretching lineation commonly indicates the direction of transport when projected onto the shear plane. The relation of fold hinges and the type of lineation. Stretching lineation most reliable for transport direction. It is the easiest to interpret for kinematic analysis. It forms by the progressive deformation like mineral lineation, mineral stretching, grain alignment, ambiguous lineation, fold axis, granulation, intersection lineation. It represents unrelated deformation superimposed final stage of progressive deformation, kinematically informative, relationship of transport direction, variable orientations relative to stretching lineations. As you can see in the figure 13.14a, uh, fold axis and the lineations has a perpendicular relationship, and in the second diagram it has the parallel relationship. And in summary, lineations are most important because of their close relationship to kinematics or movement direction, and together with the foliations, they provide significant information about deformation history, bouginage, and often considered their lineations in other structures that deserve closer attention. Lineation can be stressed objects, silicon sites on slip surface, lines of intersection between planar and non-physical lines, such as fold axis. In plastic regime, lineation form penetrative fabric along L fabric or together with foliation LS fabric. A very profound stretching lineations may indicate prolate strain. Many lineations are closely related to strain or slip and therefore to kinematics. Using a lineation as an indicator of transport direction, movement direction requires that we understand how the lineation formed. Thank you. This For further reading or to understand, I recommend Fosson's Structural Geology, the source of two material. Thank you for your attention.